Hello everyone, my name is Tanusavellan Analytikumaran and today I would like to give a short introduction about truss. Truss is a structural component typically made from straight pieces of metal or timber, strategically arranged to form a series of triangles within a single plane. This configuration provides stability to the structure, enabling it to withstand substantial external loads over a considerable span. The individual elements of a truss primarily endure axial tension or compression stresses. Trusses has widespread application in the construction of buildings, bridges, and roofs, where they offer essential structural support and stability. Additionally, trusses play a crucial role in the design of certain aircraft components, providing a lightweight yet strong framework for various purposes. Furthermore, in some cases, vehicle chassis and frames incorporate truss arrangements to optimize strength to weight ratios, thereby improving overall vehicle performance.
There are many types of trusses have been utilized in construction to meet specific engineering needs. Examples of these trusses include the Kim post truss, which is characterized by a central vertical post, and there is Queen post truss, which invented with two vertical posts for added stability. Hoy truss that employs diagonal and vertical members for medium to long spans. Other than that, thread truss, Warren truss, and Pink truss also offer alternative with distinct arrangements of diagonal and vertical components. Characteristics like span length, load requirements, and architectural consideration also play a role in the selection of truss design, which demonstrate the adaptability and diversity of trusses in contemporary constructions. In structural engineering, the analysis of trusses is essential for evaluating the internal forces and reactions within truss systems. Two primary methods are commonly employed for this purpose, which are the method of joints and the method of sections. According to Huggers and Merrill 2020, the method of joints is a static principle stating that all joints in a truss must be in equilibrium. This means that forces on truss members of each joint must combine at the joint to equal zero for all joints. Meanwhile, method of sections involve dividing the truss into sections by cutting through the selected members and analyzing the section as a rigid body. This method offers the advantage of revealing internal member forces in the sections where cuts are made, while ignoring the internal forces in the other sections.
Hi everyone, my name is Tuton Ang and my normal matrix is 223504 and I'm going to talk about truss design. There are two types of truss design proposed and I'm going to talk one of the truss design. Both truss design are inspired by the variant truss type with little modifications. For the first truss design, the outer shape is a rectangle shape and there are three right triangles with one right angle which is 90 degrees and two acute angles of 45 degrees. There are 5 points, point A, point B, point C, point D and point E, where the distance from point A to point B is 10 meters and the middle point of the truss is located at point D. So as you can see on the slides, this is the first truss design. Next, I'm going to talk about the calculations for three conditions where the 2000 Newton loads is located at point A, middle point, point D, and point B. Before we start the calculations, we assume tension force experienced by the beam is positive and force going right for Fx is positive and force going up for Fy is positive. After that, we just do normal plus minus calculation based on the free body diagram. In the end, I compound all the force result into table form for clearer observation. So from the table, we can observe that the highest force was sustained by the pin with a recorded value of 4165.18 Newton among all the forces. So for safety concern, the force will be used as the standard values to be utilized in minimum design beam strength calculations with an assumed value of 1.5 as safety factors. In this case, the safety factor is 1.5, indicating that the beam has 1.5 times the strength needed to support the applied load. The minimum strength of every beam will be calculated in order to choose suitable types of material for each beam. So from the table, we also noted that the first structure also consists of two zero force members, which are FCD and FED. So these two zero force members are used to stable the structure.
This will be the second trial design proposed by our groups. As seen in the diagrams, it's a symmetrical structure composed by three triangles, which two of an angle of each triangle to be 45 degrees Celsius in 45 degree, and another one to be 90 degree. And there will be an AX and AY at the point A and also MB at the point B. So first of all, we need to calculate the length EA, and also since EA equals to DB equals to DC, and then we can calculate that all the slanted length of the line of the beam will be 3.5355 meter by using 2.5 over cos 45. And next we need to proceed to the weight of wind distribution. In our projects, we assume that we will make an assumption of beam weight distribution to be 10 kilogram per meter, and here we can get the force of each joints. And later on, we need to go and calculate the MB calculations. Since the calculation by using a summation of moment at A equals to 0, we didn't use it we didn't use a summation of moment at joint B, because if let's say we use a joint B, we need to calculate the force at joint A, right? So it will be very complicated since it has an AX and AB to be unknown. So we use joint B as alternative instead. So from here we get that the FTB and also FCB to be compressive and tensile force respectively. And next, the same thing happened to joint D. So we found out that FCD and FED to be compressive force and tensile force respectively also. And joint C, FEC to be compressive force and FAC to be tensile force. And the same thing happens again for joint E, same calculation using a summation of Fy and Fx. But however, for this one, for joint E, right, from a summation of Fx, we found that the FAE have a greater compressive force compared to the FAE found in the summation of Fy calculations. So we'll be using a greater force, which is the FAE force from a summation of Fx for the further calculations. And next will be joint A. And the same thing happens again by using FAE from the summation of Fy and from summation of Fx from the previous joint. And then we get an AY and AX to be 1162.6695 and AX to be 1763.9135. And for the 2 kilo on center, right, as the previous one is a 2 kilo on the joint A at point A, and for this one is 2 kilo on the center, which is point C. Actually, it's just the same thing, but however with different variations, in which that for NB calculation we need to add a negative 2000 times 5. So our NB will be increasing, and for joint C, for our joint C, right? For our joint C, we need to include the negative 2000 kilonewton, since our load now is at the center, which is joint C. And for our joint A, we need to remove a negative 2000 newton. So we're getting an AX and AY. However, our AY to be negative instead of compared to the positive value at the previous calculations. And the same thing happens for the right side, 2 kilo on right side. For this one, we need to increase we need to adjust the MB by inserting 2000 times 10 instead of 2000 times 5. Times 5. And for the joint B, we need to include the negative 2000s. But for joint C, we need to remove it. And for joint A, we also remove the negative 2000s. And then we will get the AY to be negative again, and for AX to be positive, as the same as the all three examples, all three conditions. And this is a comparison graph for all three conditions. And we can find that when it's at the when the thing is at the load, right, most of the beam exhibit the greatest force compared to the other two conditions. And since for the sake of convenience, we'll be assuming that we will be using the greatest force from FAE when the load is at the center, which is 5x to be the value, to be times with the safety factor, in which we assume it to be 1.5, and then we get a 8527.5176. And this one we'll assume that and we'll be using this Newton as a basis for calculation of the cost requirement for all of the beam, since it's impossible for us to buy this to purchase a beam in strictly follow the strength demand of each beam. Since that one will be bringing in more cost, and also most of our supplier they will prefer the client to purchase in bulk for only one type of the strength demand.
So I will present about the costing calculation of the two cells. So the material used is steel, and carbon of steel is 2,583.93 ringgit per ton, which is equal to 2.584 ringgit per kilogram. So we assume thickness of the steel is equal to 0.05 meter. Then we assume average density of steel equal to 7,900 kilogram per cubic meter, and the mass density is 50,000 SI, which is equal to 344.79 megapascal. So with the density we can find the maximum force, which is 376 kilonewton. We can use that force for the calculation of volume, because the maximum force of steel is far more higher than force reaction of its member when the force subjected to it. So we got density from volume is 15.52 H kilogram, which is the length of each member of the torso. So next we will calculate the total cost of the design. So for the design one, we got to calculate the weight of the steel first, the total weight of the steel, and we find the price of the. So design one, we got 0.0 685.0528 kilogram, and with total cost 177.0.8 ringgit. So for the design tool, 452.283 kilogram, and the total cost is 1,168.7 ringgit.
Greetings, everybody. My name is Dinesh Subramaniam. My matrix number is 225700. Today, I'll be talking about selection of materials. The selection of materials should consider factors such as the span length, load requirements, environmental condition, and budget constraint. Additionally, local building codes and regulations play a crucial role in determining the acceptable materials for truss construction. Consulting with a structural engineer or other relevant professionals is advisable to ensure the chosen materials meet safety and performance standards for a specific project. Steel is a highly suitable material for trusses due to its unique combination of properties, making it well suited for various structural applications. Here are several reasons why steel is commonly used for truss construction. The first one will be strength. Steel is known for its high tensile and compressive strength, making it capable of supporting heavy loads over long spans without excessive deformation or failure. Second will be ductility. Steel exhibits a high degree of ductility, allowing it to undergo significant deformation before reaching failure. This characteristic is crucial for absorbing energy in the event of sudden loads or dynamic forces, contributing to the overall stability and safety of a structure. And the last one will be durability. Steel is resistant to many environmental factors such as corrosion, rust, and degradation. Protective coatings can be applied to further enhance its durability, making it suitable for both indoor and outdoor applications. That's all from me. Thank you.
In conclusion, prioritizing safety is important for maintaining the structural integrity of the truss. This involves designing the truss to indoor expected loads while preserving its stability, strength, and overall performance. Comparing Design 1 and Design 2 of the truss, Design 2 is chosen to propose to the top management. It has higher force that the beams can sustain, which is 5,685 Newton with 8,527 Newton of the minimum design beam strength. Based on the material used, a steel beam with a thickness of 0.05 meters and assumption of 10 kg mass per meter has the capacity to endure a maximum force of 676 kN. This resilience surpasses the 5,685 Newton highest force reaction in Design 2 just now, making the structure is safe to use in construction. So this affirms that the selected size for the steel beam is appropriate to prevent any instances of overloading. In terms of stability, Design 1 is said to be more stable since it has 0 force members, but Design 2 is also stable because it is characterized by diagonal members that form equilateral triangles. These multiple diagonal members includes the redundancy in the design. This redundancy enhances the overall stability of the truss structure.
Well, considering the cost aspect, it's essential to take material cost into account. Both Design 1 and Design 2 utilize steel, the cost-effective and durable material that helps to adhere to budget constraints. The total cost for both designs are 1,770 ringgit and 80 cents and 1,168 ringgit and 70 cents, respectively. This indicates that Design 2 is more preferable than Design 1 as it can sustain higher force while remaining cost efficient. Looking at ease of manufacture, assembly efficiency plays a crucial role. Designs that allow straightforward assembly and installation reduce manufacturing time and associated labor costs. However, in the case of Design 2, which forms equilateral triangle, there is a requirement for bending metals at angles of 45 and 90 degrees. This necessitates the use of special equipments like shears, manual bending machines, and hydraulic bending machines, contributing to increased manufacturing costs and making the process somewhat burdensome. Additionally, the use of machinery adds to labor costs as workers are needed to operate and assemble the truss mechanism parts.